Hello, Ankush. Am I audible now? Ankush, Ankush Chavan. Am I audible? Ankush, am I audible now? Okay, thank you, Sairaj, Yashraj, Neha. Thank you. Okay, okay. So you are able to see my board. Okay, and the plan of the lecture is written there. So what we had discussed was a derivation of exergy of a closed system. So if you see the blackboard, I had written the expression of a closed system which was derived earlier. The expression for exergy or available energy of a closed system, which you need to remember. Okay, I u minus, this is also called as availability function, u minus t naught s plus p naught v. U minus t naught s plus p naught v is availability function. Okay, u minus t naught s plus P naught V minus U naught minus T naught S naught plus P naught S V naught. Okay, so this expression which I have written here, that expression availability function. If I want to calculate if a closed system like a piston cylinder arrangement, if there is a closed system like a piston cylinder arrangement, okay, and this system is at a certain state which is given by the pressure P, the volume V, and temperature T, then using this expression which is written on the board, okay, you can calculate the exergy of this closed system. Okay, I hope this is clear to you that how the exergy is calculated. In the today's lecture, what I plan is I plan to derive the exergy of a steady flow system. Okay, and the concept of second law of thermodynamics. So I hope you had watched the video. Kindly go through those videos and revise. I would be teaching you now. Expression for exergy of a, okay. Uh, the expressions for available energy or what is also known as exergy of a steady flow system of a steady flow system. Okay. This is a pretty simple expression. If you had understood the derivation of the closed system, then this would also be not difficult to understand. Okay. From the examination point of view also, but even conceptually also it is very interesting. Let me tell you what is a steady flow system. You have already derived the expression applying the first law of thermodynamics to a steady flow system. So let us say that this is a steady flow system, meaning that it is an open system whose properties remain unchanged with respect to time. Okay. So this, let us say this is a section 1.1, which is the inlet section, and the properties at the inlet are U1, which is internal energy, and P1 V1 is a flow work. Let us say that the kinetic energy is half C1 square and the potential energy is just GZ1. Okay, where Z1 is the elevation from reference. Okay, and let us say that this is the state 2, which is the outlet of this, and this state is again at having a property. At the state 2 you have the fluid having the properties internal energy is U2, the flow work at the section 2 is P2 V2, the kinetic energy is half C2 square, and potential energy is, let us say, GZ2. Okay, And let us say that there is a heat transfer to the system, which is Q, and this system performs certain work, which is the shaft work. Okay. So this we had already written, drawn this figure, okay, for a steady flow system, where I had considered a control volume. This is the dotted line is a control volume, because you know that for analysis of uh, open system we use a control surface in which there is an enclosed volume, okay, control volume, and entry to this control volume is via the section 1 and exit from this control volume is via the section 2. So if you apply the first law of thermodynamics, which is nothing but the energy balance to this system, okay, what you get is nothing but the steady flow energy equation. So if you write the first law of thermodynamics for the system, what you get is the steady flow energy equation. And if you remember the steady flow energy equation, that equation is m dot into, or m into, depending upon whether you are expressing it in terms of per second or per kg, u plus p u1 plus p1 v1 plus half c1 square plus g z1 plus q, which is the heat transferred, is equal to m into u2 plus p2 v2 plus half c2 square plus gz2 plus shaft work plus the shaft work, okay, mechanical work. Now this equation is called as the steady flow energy equation, okay. Now I am interested in finding, so this is basically, it gives you the energy output, net energy output from this any system using this, or this is basically an energy balance equation. Now I am not interested in energy, I am interested in available energy or exergy, okay. So if I want to just simplify this derivation, let me neglect this, let us say this is negligible, I will assume that this is negligible. So this becomes uh, m into h1, okay, this is for derivation purpose, I am simplifying this, is equal to m h2 plus w, okay. So this is nothing but m into h1 is capital H1 plus q is equal to h2 plus w, okay. So this is not a very difficult thing to understand. How do we get this expression in terms of enthalpy? We get this expression in terms of enthalpy for a steady flow system. Neglecting this for simplicity. when it is environment, so we don't calculate a useful work, or the useful work is equal to the shaft work in this case. Because why? Because it is an open system. Okay, so the useful work is the shaft work in this case because it is an open system. Now let us calculate the W shaft max. So W shaft max, if I want to find, then I need to rewrite this equation first. So it would be H1 plus Q is equal to H naught now. Please note, this is H naught now. And then if it is H naught, then this becomes F shaft max. This becomes W shaft max. Okay, so let us call this as equation 1. Let us call this as equation 1. Okay, now if I want to find this, if I want to find let me rewrite this. Okay, just rewrite this equation 1. So W shaft max will be equal to W shaft max will be equal to H1 minus H naught plus Q. Okay, so let us call this as equation 1. Let us call this as equation 1. Okay, instead of calling this as equation 1, I will call this as equation 1. Right now, uh, Indicate. So this is the hope this is clear to you. Audible now? Am I audible now, Anamta? Hello, Yugandhara, Yashraj. Okay. Okay. I'll repeat this, Yugandhara. From which point you want me to repeat, Rushali? From which point I was not audible. Rushali, Neha, Ananta. From which point should I repeat? Okay, from equation 1 and 2. Okay, I'll redo this whole thing. Uh, so what we are supposed to find is the exergy. Okay, we are supposed to find the exergy of a open system, and I'm taking a special case of open system, that is a steady flow system, right? Now finding the exergy of a steady flow system or an open system is what? Finding the exergy of a steady flow system or an open system means you need to find the maximum work potential. You need to find the maximum work potential. Now maximum work potential is what? Maximum work potential is when you will get the maximum work potential, you will get when you will get the maximum shaft work, and when you will calculate the maximum work from this heat transfer Q. Okay, heat transfer Q. So let us first. नहीं आ रहा, अभी आने लगा था. हेलो, हेलो, हेलो. Okay. So maximum shaft work is the W shaft max plus, sorry, W shaft. When you will get the maximum shaft work, you will get the maximum shaft work only when you'll get the maximum shaft work only when the state 2 becomes the dead state. Okay. So I can rewrite this H1 plus Q is equal to H2 plus W shaft as H1 plus Q is equal to H naught plus W shaft. H1 plus Q is equal to H naught plus W shaft. Okay. So W shaft is equal to H1 minus H naught plus Q. This is equation 1. W shaft is equal to H1 minus H naught plus Q is your equation 1. Okay. This is equation 1 is what? H1 minus H naught plus Q, which is equation 1. So I hope that W shaft max is clear to you. Whether this W shaft max is clear to you all? W shaft max is clear to you all? Whether W shaft max is clear to all? H1 minus H naught plus Q. Whether this equation 1 is clear? Yes or no? Rushali? Yugandhara? Whether equation 1 is clear? Neha, Anamta, Yashraj, Ritvik, Yash More. Whether the equation 1 is clear to you? Okay, yes, Rushali has got it. Okay, thank you, Anamta. So now let me go to the equation 2. Let me go to the equation 2. Now, what is this equation 2? Equation 2, I want to find the work potential of this cube. Okay, so what I do is that I run a Carnot engine between T naught and T, and that Carnot engine work is nothing but Q naught minus Q. So this Carnot engine work is Q naught minus Q by energy balance, right? This Carnot engine work is Q naught minus Q by energy balance, and by applying the second law of thermodynamics, Q naught by T naught is equal to Q by T. Q naught by T naught is equal to Q by T. So the second equation is Q naught minus Q is WC, and the third equation is Q naught by T naught is equal to Q by T. Second equation comes from the energy balance, that is the first law, and the third equation comes by applying the second law of thermodynamics, that is Q naught by T naught is equal to Q by T, which gives you what it gives you from 2 and 3. From 2 and 3, what you get is WC is equal to Q by T naught minus Q. Okay, whether the equation 4 is clear. Let me know whether the equation 4 is clear. Let me know whether the equation 4 is clear to you. Okay, thank you, Rushali. So the equation 4 is now with you, right? So I have now equation 1 and 4. Okay, I have now equation 1 and 4. So what I do is now I want to find the available energy. As I said, the available energy is the maximum work potential which you get from the addition of the maximum shaft work with the Carnot work. Now it is simply a question of adding these two equations. So I'm just adding the equations and rewriting this and getting the final expression. I hope this is clear to you. Okay. So hopefully for all this derivation is clear. Okay. Rushali is saying she has got it. Others also I want whether you understood this derivation. Yugandhar. Have any doubts? Okay, the video is already this Exergy analysis of the close open. Okay, only the video which is recorded. H1 and H2 has taken E and E naught, which E is then it includes the enthalpy and the kinetic energy and potential energy. Okay, so don't be confused with the notations which he or me. I am using different notations. That hardly makes any difference. So conceptually, the video has been floated on the second law of thermodynamics. So sorry, just revise that again. If you have any doubt, okay, you might you always have the video to refer to. Rushali? Hello, hello. Okay, okay. Now I'm audible. I hope I'm audible now. Okay, thank you, Rushali. Thank you, Dheeraj. So let me discuss this concept more. This concept is about the second law efficiency. The first law efficiency is the energy efficiency. Okay, so if you consider an engine, okay, if you consider an engine, for example, so for an engine, what is the first law efficiency? For an engine, what is the first law efficiency? Can somebody tell me? If it's a heat engine, what is the first law efficiency? Mohan, what is the first law efficiency for a heat engine? Anybody? Can anybody tell me what is the first law efficiency for a heat engine? Any answers? What is the first law efficiency for a heat engine? No idea? Okay, the first law efficiency for a heat engine is the energy output, which is work, and energy input, which is heat. Okay. So the first law efficiency of the heat engine is the energy output of the heat engine upon the energy input to the heat engine. Okay. Now, what is the energy output of the heat engine? The energy output of the heat engine is W. Heat engine, the useful energy output is W upon the energy input, which is heat supplied QS. So this is the first law efficiency of the engine. This is the first law efficiency of the engine. Now, what is the second law efficiency of the engine? Second law efficiency of the engine is the net exergy output. This is the net energy output. Okay, and this is the net exergy output upon the net exergy input. Net exergy input. Okay. Now, what is the exergy? What is the exergy of W? What is the exergy of W? Can you tell me what is the exergy of W? Anybody? This is the output of the engine. So, what is the exergy of W? Any answers? Any guesses? What is the exergy of W? Mohan, Dheeraj, Rushali. What is the exergy of W? Nobody knows this? Rushali, okay, yeah, correct. So Rushali is correct. The exergy of W is the work done. Exergy of W is the work done. That is, W is the exergy of, means W is the exergy, right? So W is the exergy. So exergy output is W. What is the exergy of this input? What is the exergy of this input? Input is heat. So what is the exergy of this input? What is this exergy of this input? So the exergy of this input is, can anybody tell me what is the exergy of this input? Exergy of this input is efficiency of Carnot into QS. Efficiency of the Carnot into QS, where the Carnot engine is operating between T and T naught. Okay, so exergy of this input, that is QS, is efficiency of Carnot into QS. Okay, so this is equal to, if you just rewrite this, this can be rewritten as W upon QS upon efficiency of Carnot. Okay, so for a heat engine, this is nothing but first law efficiency upon the Carnot efficiency. I hope this is clear to you. Okay, what I have done is that I am finding the second law efficiency, which is also called as exergetic efficiency. What I'm calculating is the second law efficiency, which is also called as exergetic efficiency. I had written first the expression for first law efficiency, which is the energy efficiency, What is energy efficiency? Energy efficiency is energy output upon energy input. What is exergetic efficiency? It is exergy output upon exergy input. What is the exergy of W? Exergy of W is W. What is exergy of W? Exergy of W is W. What is exergy of heat? Exergy of heat is efficiency of the Carnot engine into QS. So this becomes W upon QS upon efficiency Carnot. W upon QS is the energy efficiency. So energy efficiency upon Carnot efficiency. So for a heat engine, if you want to find the second law efficiency, then the second law efficiency for a heat engine can be obtained as efficiency law efficiency upon the Carnot efficiency. Is this clear to you? Tell me if it is clear. Whether this is clear to you, what is the second law efficiency? Mohan, Dheeraj, Neha, Parikshit, Yugandhara, Anamta. Whether this is clear to you? Tejas is saying he has understood. Rushali, Neha, they are saying they are understood. I hope everybody has understood this. Yashraj has understood this. Parikshit has understood this. Okay. Others, Mohan, Dheeraj, whether you understood this? The second law efficiency for heat engine. Second law efficiency for heat engine. Have you understood this? Okay. Jay has understood. Anybody who has understood this? Okay. Many students are saying they understood this. Mayuri Hire has understood. Mayuri has understood. Rushali has understood. Others, have you understood this? Abhay has understood this. Okay. So what we had discussed now is how to calculate the efficiency of a second law efficiency of a heat engine. Okay. How to calculate the second law efficiency of the heat engine, right? Now let us say that we are not talking about a heat engine, we are talking about some heat exchanger. Okay, some heat exchanger, like say we are talking about a solar collector. Okay, we are talking about a solar collector. So in that case, suppose I am talking about a solar collector. In that case, how do you calculate the second law efficiency? Okay, Mayur. Okay, sorry Mayur, but why you have put Y there? Mayur, and why was unnecessary, so I read it as Mayuri. Okay, so if you are Mayur, it is okay. So just like Jay, you are Mayur. Okay, all right. So let me continue with this second law efficiency term. Let us say that we are dealing with let us say that we are dealing with uh, a compressor. Okay, let us say we are dealing with a compressor, uh, or okay, or a turbine. Let us say we are dealing with a turbine. Turbine. Okay, so you know that turbine produces work, right? Turbine produces work. So from the energy angle, how is this work produced? Can anybody tell me why you are getting work from a turbine? Any answers? Why we get work from the turbine? Why do we get work from the turbine? Any answers? Mayur, Hire? Okay. But which energy, Parikshit? Which energy conversion? What is converted to work in turbine? Parikshit? What is getting converted to work? Parikshit? Okay, all right. Let me explain you that. What is getting converted to mechanical to electrical? No, no, no. In turbine, what you are getting is no, no. I am talking about a steam turbine or gas turbine, Rushali, not water turbine. Rushali, I am talking about a steam turbine or gas turbine, not water turbine. So not heat to work. Kunal, it is wrong. It is not heat to work which is getting converted in the steam turbine. What you are getting is what is entering the steam turbine is, or gas turbine also, is the flow work and internal energy. Okay, and what you are getting out is U2 plus P2 V2. So basically, neglecting the kinetic energy and potential energy, what you are getting, the work output you are getting it as H2 minus H1, H2 minus H1. So it is basically the पाटील सर मी लेक्चर मध्ये नंतर कॉल करतो. So what you get is the work you are getting as a difference of enthalpy. Okay, the difference of enthalpy. So this is the work. Okay, this is the actual work. Hello. Yeah. So what have you got this? That why you get work from the turbine, Parikshit? You are getting the work from the turbine because of the enthalpy difference. You are getting the work from the turbine because of enthalpy difference, right? Now, what is the, this is the exergy output. Okay, this is the actual work which you are getting. This is the actual work which you are getting out of the turbine. Okay, but potential, the potential, maximum work potential is will be more. Okay, maximum work potential of this energy streams, of this fluid which is entering and leaving the turbine, would be more than the actual work which you are getting. Okay, so in other words, the second law efficiency, for the steam turbine would be the actual exergy. Okay, the exergy output, this is the exergy output, and the exergy input, which is what, which is the maximum work potential of the energy stream. So exergy input to this steam turbine is the maximum work potential of this energy stream. That is H2 minus H1 is the actual work. But what is the maximum work potential of, because this is a steady flow system. This is a steady flow system. Okay, so maximum work potential for a steady flow system we had already calculated. What is that? We had calculated that the exergy of this H1 would be, what is that? H1 minus T naught S1. Okay, and what is this exergy of this? It is H2 minus T naught. Are getting this or no? Okay, S2. So this, let me just erase this, just a minute. Okay. Let me not confuse you a bit, because this is a bit more challenging. I'll just, instead of writing the expression, I will just say that there is some exergy of this stream coming in. There is some exergy of this stream coming in. This is some exergy here, and there is some exergy here. Okay. So the net exergy input would be exergy at 2 minus exergy at 1. Exergy at 2 minus exergy at 1. So this net change in exergy, okay, this net change in exergy would be the maximum work potential of this steam turbine. Okay, maximum work potential of this steam turbine, and obviously this has to be calculated. This next net exergy input has to be calculated with reference to the dead state. Okay, so simply what it means is that if it is an open system, you need to find the available energy of the streams, and you need to compare it with the exergy, the actual work. So actual work upon the maximum work would be the second law efficiency of a steam turbine. Similarly, if it is a compressor, you need to compare the actual work with the minimum work. Why is that so? Because see, what we are trying to get from the second law efficiency is we are trying to figure out how much of the potential, we are actually able to realize. Okay, we are not calculating the input and output. Okay, we are not calculating the input energy and output energy. We are in a way calculating what is the reversible work, okay, and the actual work comparison. So reversible work comparison and actual work comparison, that difference, which is nothing but the irreversibility or exergy destruction, is calculated from the second law efficiency. Okay, I hope it is clear to you. This would be more clear when we solve the numericals, but for the time being, let me just again go to the first expression. Let me tell you that second law efficiency and first law efficiency, what is the difference? First law efficiency gets you the comparison between the energy output and energy input, whereas the second law efficiency gives you a comparison between the exergy output and exergy input. So first law efficiency calculates the energy losses. First law efficiency tells you the energy losses, whereas the second law efficiency indicates the exergy destroyed, exergy destruction. Okay, so that is the difference. First law tells you where is the energy being lost. Okay, means how much of the energy is not converted to useful output. That is what the first law tells you, whereas the second law tells you how much is the exergy which is destroyed. Okay, and how much of the potential, how much of the maximum work potential one is able to achieve. Okay, we are not comparing the input to the output when you are talking about exergetic efficiency. Please note, okay, we are not comparing the energy input and energy output in the second law efficiency. We are comparing the maximum work potential and the actual work potential realized when you are talking about the exergetic efficiency or second law efficiency. I hope this is clear to all of you. So those who are attending this lecture, Parikshit and all those, this obviously you have understood. Okay, right? So is this clear? Okay, Parikshit is saying it is clear. Jay is saying it is clear. The concept of second law. Okay, Neha, for Neha it is clear. So please listen to the videos. Okay, also along with the discussion which we are having in the class, right? And that completes. Let me just announce that that completes the portion of Chinmay. Thank you. That completes the portion of Exergy analysis. If time permits, we would solve one or two numericals maybe on this two concepts, that is second law efficiency. You would be solving some numericals, and we would be solving one numerical on steady flow system, exergy of steady flow system. Okay, so that is left in the exergy chapter. We would be starting with the properties of steam chapter, and I want you to either download online the steam tables, or if you are able to purchase a hard copy of the steam tables, that is also good. Okay, so my suggestion is, you just try to get hold of steam tables. Steam tables means nothing but the properties of steam are tabulated. Okay, you will find that online steam tables are also there, but just to get you some idea about the steam table properties, steam properties, I want you to purchase the steam tables from the market. If you are able, if you are having access to the bookshops, so kindly purchase steam tables, okay, from the market. Or if you are having some books which are having the steam tables with you, that would also do. Okay, so from the next class, if I will not be taking the numericals, in from the next class or next to next class, we would be doing with the new chapter, that is properties of steam. And after properties of steam, we would be dealing with the vapor power cycles. Okay, meanwhile simultaneously you would have the boiler theory portion covered by Professor Pillai, and once the steam properties are done, we would also be dealing with the boiler energy balance. Okay, boiler energy balance, right? One more chapter would be remaining then, which is fuels and combustion, which would be covered simultaneously. Okay, so thanks for attending these extra lectures. I know that it is too demanding for you to attend the fourth lecture, but because we are running also out of time, and I want you to internalize this concept before Diwali, okay, so that you would enjoy these festivities more. Okay, so I scheduled an extra lecture today. So thanks for all those who had the 765 plus students have joined. Okay, and the others who have missed this lecture, for whatever reason, they are advised to refer to the videos which have been shared to you on your WhatsApp groups. Okay, and get these concepts clear. Thank you for joining. Thank you very much, and sorry for the audio problems which I had from my side. Okay, have a good day and happy Diwali to you.